Have you ever heard that nature speaks through numbers? Are you curious to know what does that mean? If so, then stay with us because today we are giving some insight on such a topic. In this video, we will discuss how to model information through numbers and how it is exchanged by means of signals. More precisely, we will give an overview on continuous and discrete domain signals. We will introduce concepts such as sampling and quantization, and we will touch upon the frequency representation of signals in a simple and intuitive way. Hi, and welcome to Control Theory in Practice. What is the role of information in our lives? Well, as Shannon elegantly plays it down, information can be seen as a resolution of uncertainty. And obviously, the less you are uncertain on something, then the easier it is to take decisions. But let's clarify with an example. Imagine that you are a detective investigating on a crime. The more you investigate, which means the more you increase available information, then the smaller becomes the short list of potential criminals, which means to reduce uncertainty, and then it's easier to spot the criminal, which means it's easier to take a decision on who to send to jail. One thing that you can do in your everyday life to increase the level of information almost for free is to try to quantify it, which means to stick numbers to it. And if the numbers are uncertain, then just use the ranges of numbers. Can you see the difference if I say, it's going to take some time, or it's going to take 5 days, or, well, it's going to take between 5 and 10 days? I have a secret for you. Sometimes using ranges is the best. Try to ask your project manager what he or she thinks about that. Can you see how in making the extra step to discuss things in terms of numbers help us in setting sharper targets and clearer expectation? And most importantly, it does not leave any room for misunderstanding or mystification.
Yes, but there are many things that you cannot express just through numbers.
True, but it is also true there are still many things that you can quantify through numbers if you only make an extra effort to think a little bit out of the box. In fact, you could quantify your mood, sustainability levels, team performance, as well as classical quantities such as the level of satisfaction of a customer, the revenue of a company, or classical engineering stuff like temperature, pressures, angle, and so on. But what if the information is very complex? Then use more numbers. For example, if we want to model a color, we can use 3 numbers where one number represents the amount of red, one represents the amount of green, and one represents the amount of blue. Or, if you want to model your team performance, you could use, for example, one number to represent the delivery rate, one for representing some quality metric, and another one to keep track of the cost. We talk about information. But information is not something that is static and just stay here, right? At some point, we have to exchange it with someone else. So the question is, how information is exchanged in the world? Once more, let's observe the greatest source of inspiration ever, Mother Nature. We can see that in nature, information is always exchanged through some signaling mechanism. Birds chirp, peacocks show off, and even our tummies send signal when we need food. But now, if we model information through numbers, how shall we model signals? Well, the easiest is to model them as a stream of numbers, but we have to pay a little bit of attention here. To model a signal, we need at least 2 sequences of numbers. One is independent and the other is dependent. For example, the bird chirp has one sequence of numbers representing the time and one sequence of numbers representing the sound amplitude. Signals coming from our tummy are represented by a sequence of number representing time and another representing the amplitude of the cramps. Needless to say, but the same concept applies also to more classic engineering quantities, such as temperatures, pressures, or company revenues. They are both signals, and it's easy to spot an independent and a dependent sequence of numbers. What we have seen so far are examples of one-dimensional signals, because the information that we wanted to convey was made by one number: temperature, sound, company revenue, and so on. But what if the information is made by more than one number, like for example in the color example that we have just seen? Well, in that case, a signal is a sequence of a tuple of numbers parameterized by another numbers or by another tuple of numbers. I know, that was tricky, so let's make an example. Assume that we want to send some information to someone by means of displaying a digital image. Then, according to our weird reasoning, we are dealing with a signal, because we are transferring information, right? And according to our even more weird reasoning, we should be able to spot an independent and a dependent sequence of numbers, right? Let's see how to do that. We all know that a digital image is made by a grid of pixels. The whole pixel grid can be viewed as a sequence of tuples of two numbers. And this is our independent sequence of tuples of numbers. The dependent sequence are the RGB values associated to each pixel of the grid. Here each tuple has three numbers. In this case, our signal associates a RGB value to each pixel. Now, given that the dependent sequence was not made by one number, but it was made by a tuple of numbers, then we talk about multidimensional signals. We call signal domain the set of all the values of the independent variable. Let's take the chirp signal. Time can be the independent variable, and a possible domain can be the time between 1 o'clock and 1 o'clock plus 10 seconds. Or if we want to consider the company revenue example, we can consider again time as independent variable and the first 3 quarters of 2023 as the signal domain. If instead of time we consider space as independent variable, like we have done in the digital image example, then a possible domain could be a 30 by 30 pixel array. Note that the independent variable is something, like time or space or whatever you like, whereas the signal domain are the values of such variable during our observation period, like for example 10 seconds or 3 quarters or 30 by 30 pixel array. With a slight abuse of terminology, we can distinguish signal domains in continuous and discrete. You can think to a continuous domain as a domain that you can relate to a subset of the real numbers, like the chirp example or the temperature example that we have seen so far, or discrete if it can be related to a subset of the natural numbers, like for example the digital image example or the quarterly revenue of a company. Sometimes observing a continuous domain signals over all its domain may require too many resources. Think for example when you're watching a football match. You don't stare at the TV screen continuously for 90 minutes. That would be just exhausting for your eyes. What you do in practice is that you look a little bit at the TV screen, you take a look at your mobile, you go to the kitchen and have a beer, and yet you can capture everything that is going on the football field. But what happens if you look at the TV screen too seldomly, like twice in 90 minutes? Then you are going to miss exciting part of the match, don't you? Observing a continuous domain signal only at some points is a common practice and it is referred as sampling. For example, if we sample the signal every 0.5 units of time, then we get this representation. As you see, if we follow the dots, then we still have a good capture of the original signal. But, given a signal, if we reduce the number of observation points, then we may miss some important information. And if we increase the observation point too much, then we may just wasting resources. Therefore, the key question here is: how often shall I observe a continuous domain signal such that I don't miss too much information and I don't burn too many resources? Don't stress too much, because the answer is already given by the sampling theorem. But this is a topic for another video. To anticipate a little bit what it is, such a theorem tells us what is the minimum rate by which we should observe a continuous domain signal, such that we keep all the information therein contained and we don't burn too many resources. We have seen how to sample a signal, but something interesting happens here. Despite the signal domain now is a countable set of numbers, the value of the samples fall pretty much everywhere on the y-axis. So even if we sample, we are still dealing with a continuum of numbers. However, no one prevents us to sample on the y-axis. Such a process is called quantization. Let's start again without continuous signal and let's sample on the y-axis instead. Then let's trim our signal correspondingly to those horizontal lines. The signal values don't fall everywhere any longer on the y-axis, but only on the determined points. However, the signal domain stays continuous. But again, no one prevents us to both sample and quantize, ending up in a representation like this. Note how both the domain and the codomain are no longer continuous, but both became countable sets, and this is how information is stored in computers. Anyway, to reconnect the sample and quantization concept to our football example, we are sampling when we intermittently watch at the TV screen, and the quantization is the fact that what you see on the TV screen is a mere approximation, in terms of resolution and colors, of the real thing happening in the stadium, which is continuous. To make a small recap, we have seen that information can be modeled through numbers and can be exchanged by means of signals, and therefore signals are a stream of numbers and they can be continuous or discrete. However, there is a third way for representing signal, which is in the frequency domain. What is that? To explain that, I have to resort to the work of Joseph Fourier, who is a mathematician who lived during the 19th century. What he discovered is that by combining a number of sine and cosine waves, then you can approximate any periodic signal. The mind-blowing thing is that you can also do the other way around. Namely, starting from a periodic signal, the Fourier transform tells us what are the sine and cosine signal composing it, and can tell us exactly what is the amplitude, frequency and phase of each of those components. Why I find it mind-blowing? I can explain you through an analogy. Take a nice and yummy dish, and imagine that you have a formula such that by observing the yummy dish without any additional information, I can tell you exactly all the ingredients along with their quantity with zero error. Not like this artificial intelligence thing, you know? Now, details on the Fourier transform goes beyond the scope of this video, but there are channels like 3Blue1Brown or Veritasium that made incredibly high quality videos on the topic, and I suggest you to watch them. I'll leave you the link in the section below. But now, given that perhaps someone have noticed that I'm in the process of learning MANIM, I think that I will join the club of the Fourier Transform video maker soon, so stay tuned. For now, I'm only interested that you understand that a signal can be decomposed as a sum of sine and cosine waves through the Fourier transform. We arrive at the end of this video. What we have seen so far? Well, we started by simply observing the world around us as is in a non-invasive way and without trying to crack any physical law.
Like engineers and software developers often do.
Then we borrow some off-the-shelf tools from mathematics to shape all of that. We ended up in using numbers to model information and stream of numbers to represent signals, and we further introduce some possible way to look at signals. Although we are not seeing yet tangible things that we can use to our everyday job, we are still providing the building blocks for what is coming later. In fact, if you keep well in mind this concept, when we will talk about PID control, MPC, Kalman filter, and so on and so forth, then everything will go like a breeze. Having said that, I am Ubaldo, this is Control Theory in Practice, and if you like the video, thumbs up and subscribe, and we will see you next time.